This is Geometry, Unit 7, Day 3. We're looking at the converse of the Pythagorean Theorem. We know that Pythagorean Theorem says if you have a right triangle, then you can use c squared equals a squared plus b squared. But now we're going to work the other way. If c squared equals a squared plus b squared, if that works, then you know for sure it's a right triangle. So the converse to the Pythagorean Theorem helps identify if a triangle is a right triangle. So if you need to know if it's a right triangle, see if the sides help support c squared equals a squared plus b squared. So if the square of the lengths of the longest side is equal to the sum of the squares of the other two sides, we can't call it hypotenuse now because we don't know it's a hypotenuse, but it's definitely the longer side. Then the triangle has to be a right triangle. In other words, if this works, then the triangle is a right triangle. So here's our example. We're given a triangle. We're given all the numbers. What we need to do is identify if this is truly a right triangle or not. Are these perpendicular on the sides? So what we're going to do is take the longest side. And if you're not sure if that's the longest side, you could plug that into a calculator and see that the decimal is larger than 9. I like to put a circle because we're not sure if it's equal, less than, greater than, trying to figure out what the option is. The sum of the other two sides, well, I need to square this side also. So when you square a square root like this, you got to square the 3, and you have to square the square root. We still don't know how it compares to 36 and 81. When you multiply these two numbers out, you get 117, and when you add these two numbers together, you get 117. So now you know it's going to be equal. Because they equal, the square of the longest equals the sum of the square of the other two sides. We know that this is a right triangle. So we come over here to this other one. Here I have integers. It might be a Pythagorean triple. Maybe I could look on my chart that we learned the other time. But I'm going to take the longest side, which is 29. Compare that with the sum of the squares of the other two sides. So when I take my 29 and square it, I get 841. Compare that to 256 and 576. And this 841 is bigger than 832. So they're not equal. This one's bigger. So it's not that the triangle couldn't exist. Sure, the triangle might exist, but it's not going to form a right angle if it did exist. So it's not equal. Oh, don't forget the U. It's not equal. So, not a right triangle. Now, this is not equal. Now, think about if it's not equal. If this side was longer, if it was really long, then this angle is going to become bigger. If this side was shorter, If the angle was smaller, it's going to make this third side shorter. So we can probably start to do some predictions here. So we're going to try to classify a triangle by its lengths. We're going to identify if it's acute, if it's obtuse triangle, or if it's a right triangle. If c squared equals a squared plus b squared, if it equals that pattern, then we're going to have a 90-degree angle, which makes a right triangle. If c squared ends up being smaller than the other two, then angle C has to be smaller than 90, which makes all three angles less than 90, and it makes it an acute triangle. And on the contrast to that, if c squared is greater than, like we had up above, if c squared is greater than a squared plus b squared, then c squared has to be greater than 90, or, sorry, the measure of angle C has to be greater than 90, which makes this an obtuse triangle. So now there's three situations that can occur when we practice this. You might get an obtuse triangle, you might get an acute triangle, and you might get a right triangle. Notice that when we set this up, we always set it up with the c squared first, or with the hypotenuse, the longest side first, when we do the testing. Don't get into the pattern and say a squared plus b squared equals c squared, because if you read it backwards, it doesn't quite make the same obviousness. If c is less than, if c squared is less than those, less than means small. Acute is a smaller angle. If c squared is greater than is bigger. Obtuse is a bigger angle. So it helps follow that pattern. If you read it the other direction, it's going to read it to become the opposite, and that's a little tougher to remember. On the next page, we're going to look at a new theorem. It's called the Triangle Inequality Theorem. And the Triangle Inequality Theorem says, in order for three side lengths to form a triangle, the two smaller lengths have to add to be greater than the longest side. So that just means any three numbers don't always make a triangle. The two small ones have to be greater than the longest. If you think about that with items, if the two short sides weren't long enough added together, then you wouldn't get a TP shape. So let's take a look at some possible side lengths. If we had that length and this length, we're going to try to make a triangle with that length. Notice that when we put these together, we're trying to make a triangle out of it. Well, true, we have a triangle there, but we're not using the whole red side. So we would need to extend it out, and notice that the two smaller sides do not add up to be bigger than the longest side. So you can't really make a triangle. If you extend this out to the edge, so you can make your triangle, or even connect it, you can't make a triangle with that. It's never going to touch. But, on the contrary, if these two do add up to be greater than the third, then you can get the TP part of the triangle. That's what makes it into having an open space in between. The smaller sides have to add up to be longer than the third side. That's why it works. So let's see. Can segments with the following lengths form a triangle? That's the first question. And the second question is going to be, if it makes a triangle, then is it an acute triangle, a right triangle, or an obtuse triangle? So what we're going to do is look at all three lengths. And with all three lengths, we have to take the two smaller sides, the 2.8 plus the 3.2, and that adds up to be 6. And the question is the sum of the smaller sides bigger than the longest side? And the answer is yes. So c squared is going to be greater than, c, just c itself. I wrote that in there backwards again, sorry. The sum of a and b is larger than just c when you add them together. So now what we're going to look at is c squared and compare that to a squared and b squared. So c squared is your 4.2, and square that. Your a is going to be your 2.8 squared, and your b is going to be your 3.2 squared. So when you square 4.2, we actually get 17.64. And we have to compare that with 7.84 and 10.24. When we add them together, we get 18.08. So we know that the c squared is less than. If it's less than, then it's going to be an acute triangle. Remember, you always want the c squared to be first. Let's try this side. We're going to take the two smaller sides of your three numbers. You've got to pay attention to what numbers you have. So we're going to take our 6.1 and our 9.4, and when we add those together, we get 15.5. Now what we notice here is that the c is still less than the a and the b added together. The 11.3 is less than those two added together. That's a requirement. That's called the triangle inequality theorem. So now we're going to take c squared and we're going to compare that to a squared b squared. The c squared is your 11.3. The a is 6.1. The b is 9.4. That's not real important which way you go with the two smaller sides. So when you square this, we get 127.69. When we square, we get 37.21 and 88.36. So now we have 127.69. And this other side adds up to 125.57, and we know that 127 is greater than. So in other words, c squared is going to be greater than. So we know we have an obtuse triangle. If it happened to equal it, then we know we had a right triangle. Let's try that on this last problem. Could you use triangles with side lengths 50, 120, and 130 to verify that you have perpendicular lines? So we're looking at, if you had 50 and 120, the question is this perpendicular? Does it form a right angle? So what we can do, we can measure the length across here, which they tell us that that's going to be 130, and then we're going to test that. We're going to see if 1, does that even make a triangle, and 2, does that make a right triangle? So we're going to look at the triangle inequality theorem. And the triangle inequality theorem says that the longest side has to add up to be, or actually, the two smaller sides have to add up to be greater than the longest side. And it clearly does that. So we now know, yes, we have a triangle. So now we have to figure out what type of triangle it is. So we're going to take our c squared, our a squared, and b squared. So we have 130, 50, and 120. When we square 130, 16,900. Square 50, 2,500. And square 120, so we get 1690, or 900. And that's going to equal what this adds up to be. Here we have 14,000 and 2,000 makes 16,000. 500 and 400 make 900. So they're equal to each other. So this is an example of a right triangle. So to answer the question, do we know that they're perpendicular? If a right triangle, and we've shown that, then we have a right angle. And if we have a right angle, then we have perpendicular sides. So we've done many proofs that dealt with that order of going from a right triangle into perpendicular sides. So this helps use that process also.